Hi, PPL Navigation, Lesson 1, Part 2. Hopefully you got through Part 1. We've got a fair bit to cover, but we've still got a lot of the terms and definitions that we have to go through. So on the test, there is a few bits and pieces that's always referenced, and it's using their terms. So we go through it so that we can reference the exams. Having just sat my exam, while it was still in front of mind, I've highlighted some of the conditions and the things that we need to be able to get through in reference to some of the exam questions that I've seen. So, kick off. Statute mile, unit of length equating to 5,280 feet or 1,609 meters. Nautical mile is a unit of length equating to 6,076 feet, rounded up to 6,080 feet or 1,852 meters. 1 nautical mile is also 1 minute of arc. Kilometre, unit of length equating to 1,000 meters or 3,280 feet. A metre, base unit of length, 1 metre is equal to 3.37 feet. And that, funny enough, was on the exam. 1 foot is equal to 0.348 meters. In order for us to be able to calculate conversions between statute, nautical and kilometers, we can use the E6B or the flight computer, whichever one you have. But so that you can sanity check your answers, it's good to have a rough understanding that, for example, 1 nautical mile equals 1.852 kilometers. 1 kilometre, about half a nautical mile. 1 statute mile is 1.5 kilometres. 1 kilometre is, again, 0.621 of a statute mile. And 1 statute mile is 0.87 nautical miles. So it's just good to have that so that we can sanity check our answers when we're asked to do calculations on the E6B. So in order for us to measure distances up to 300 nautical miles with a tolerance of plus or minus 1% on the appropriate chart, we will be required to measure accurately a distance between positions so that we can create part of that information into our flight plans. Make sure you use a ruler with the correct scales in relation to the scale on the chart. So if you're given a chart with a scale of 1 to 500,000 or 1 to 250,000, make sure that the ruler you're using probably has both, one on one side, one on the other. Sanity check that, make sure you're using the right scale in relation to the scale of the chart that you're taking it off. Definitions of speed and velocity, you probably all know this, but a knot is the standard unit for an aircraft speed in knots. 1 knot is 1 nautical mile per hour. Ground speed, speed of an aircraft relative to the ground, which is also measured in knots. Indicated airspeed is the airspeed displayed on the airspeed indicator, uncorrected for errors. Please remember that it's uncorrected for errors, and measured by the pitot-static system, the aerodynamic speed of the aircraft in its entirety. Calibrated airspeed is the indicated airspeed corrected for instrument and pressure deviations and position errors. The true airspeed is the calibrated airspeed corrected for differences in air pressure and temperature density. And again, we'll show how to jump between calibrated and true using the E6B quickly. TAS tells us how quickly we're actually moving through the air when density changes due to the changes in pressure or temperature from the standard ISA conditions. The airspeed indicator no longer gives an accurate reading of our speed relative to the air mass we are flying through. The difference between speed and velocity, this came up as an exam question. Velocity is speed and direction, while speed is just how fast something is moving without us being given the direction of that movement. Ground position is determining where we are on the ground, so landmarks, flying over points of reference, usually relates to a position on the chart. Dead reckoning position is a position calculated by dead reckoning that is flying a bearing or direction for a period of time and using ground speed to figure out where the aircraft will be. A fix is a position of an aircraft at a given time determined using reference to ground features or navigation aids. For example, overhead OHAL point. The position line is a line on which an aircraft is known to be at a specific time. Could be an actual line or an imaginary line that we've drawn on our map. Place names, very obvious. Place, bearings and distance, again for position reporting, given the aircraft's position in relation to a place or location. So 10 miles west of Carterton, for example. Latitude and longitude, we did that in the last video. You should have nailed that by now, and if you've done the revision questions for lesson 1 part 1, then you wouldn't have moved on to this unless you got 100% in those, so we won't need to go through that. Position of the other aircraft's point, relative bearings and clock face methods we've done as well. Height is the vertical distance above a specified datum, the ground for example. Different to altitude. Altitude is the vertical distance above mean sea level. And just for clarification, mean sea level is the datum for measuring altitude. The average layer of the surface for one or more of the Earth's oceans is used to define mean sea level. AMSL, above mean sea level. Ground level is the datum for height, not altitude. The datum for height, ground level, obviously varies immensely due to hills and valleys, etc. Unlike mean sea level, which makes ground level unsuitable to be used as a reference for flight, but very good reference for altitude clearance heights, which we'll get on later. AGL, above ground level. Elevation, commonly used to describe the distance of an object above mean sea level. Tops of masts, hills, buildings. Definitions of altimetry. So first of all, pressure altitude is the altitude in ISA with the same pressure as the prevailing pressure on the day. And this is important for performance calculations. So to calculate, we take the difference between the standard QNH or QNE 1013 and our prevailing QNH, multiply this distance by 30 and or subtract this to our elevation to get pressure altitude. We will go into that in detail later on, but the one thing is that difference in pressures and temperatures means that our perceived altitude, if we're running with the wrong QNH or the wrong 1013.2, means that our reference in altitude will be different to other people's reference in altitude, and we will bump into each other and fall out the sky like a brick. QNH is the sea level pressure. When the QNH is set in our altimeters, we are able to determine our vertical distance above mean sea level, i.e. our altitude. And we hope that everyone who is flying within the same airspace all has the same QNH, or it could get interesting. So how we explain the effects of a change in mean sea level air pressure on the altimeter reading of a transiting aircraft. This does come up in the exam, but the definition is important. So if the aircraft is travelling from an area of high pressure to low pressure, the altimeter will read high and vice versa. So that little aid memoir is from high to low, look out below. You will hear that a lot. How we explain the effects of a change of temperature on the altimeter reading of a transiting aircraft is the, oh god, my spelling is terrible. If the temperature is warmer than ISA, the altimeter underreads, meaning that you are actually higher than indicated and vice versa. Again, remember the from high to low, look out below. Civil Aviation Rule 91.236, altimeter settings. A pilot of an aircraft must maintain the cruising altitude of flight level of the aircraft by reference to the altimeter that is set in accordance with the following. When operating at or above flight level 150, set the altimeter to the standard ISA, which is 1013.2 hectopascals. Excuse me. When operating at or below 13,000 feet, set your altimeter to the appropriate QNH zone setting or aerodrome QNH. When operating between 13,000 feet and flight level 150, set altimeter to the appropriate area QNH zone settings or advised by ATC. Pilot of an aircraft that is ascending or descending must set the altimeter in accordance with the following. 1. When ascending above 13,000 feet, set altimeter to 1013.2 hectopascals. When descending through flight level 150, set the altimeter to the appropriate QNH zone setting or aerodrome QNH altimeter settings. That's the official view as per civil aviation, and we will go through the transition altitude, transition levels in the next slide. So, as per the AIP ENR 1.7 altimeter setting procedures, this is the dumbed down version. So 13,000 feet, the transition altitude, and below, you set the area QNH zone or aerodrome QNH. So 13,000 feet to flight level 150 or flight level 160, depending on some further constraints. We don't fly in, we don't cruise in, we only transition in and out of. So flight level 150, the transition level, and above, the altimeter must be set to 1013.2 hectopascals. Please remember that number. Between 13,000 feet and flight level 150, the layer, the transition layer, is set the area QNH zone as advised by ATC. So when climbing above 13,000 feet, the transition altitude, you change your altimeter to 1013.2 hectopascals at 13,000 feet. When descending through flight level 150, the transition level, into the transition layer, you change the area QNH zone or aerodrome QNH at flight level 150. So you change to 10132 hectopascals at 13,000 feet. And when you're coming out and entering the transition layer, you set the QNH for the zone, aerodrome, or as directed by ATC. That stops us bumping into each other while we are transiting or transitioning through the levels. So it is important, everyone knows how to do it. These are very, very pertinent questions. You will get questioned around transition layer, transition levels, and transition altitudes. So you may not cruise between 13,000 feet and flight level 150, the transition layer, without ATC permission, or if you're outside controlled airspace and cannot operate at any other level. If the area QNH is 980 hectopascals or less, the lowest flight level you can use increases from flight level 150 to flight level 160. And that goes back to differences in air pressure and air density and how that is perceived on our altimeters. So this is the actual extract from the AIP. A pilot of an aircraft departing from an aerodrome where no QNH setting is available must set the aerodrome elevation on the altimeter prior to departure and obtain the appropriate altimeter settings from ATS unit as soon as possible, and in any case before entering IMC. Civil Aviation Rule 91.313 VFR cruising altitudes and flight levels. A pilot in command of an aircraft operating within New Zealand FIR under VFR in level cruising flight at no more than 3,000 feet AMSL or 1,000 feet above ground level, whichever is the higher, must, unless otherwise authorised by ATC, maintain the following altitudes or flight level. When operating at or below 13,000 feet AMSL, on a magnetic track of 270 clockwise to 089, so from west to east, any odd 1,000 feet altitude AMSL plus 500 feet, or on a magnetic track of 090 clockwise to 269, any even 1,000 feet altitude AMSL plus 500. A pilot in command of an aircraft operating within New Zealand FIR under VFR must not maintain level cruising flight at any level between 13,000 feet and flight level 150 unless otherwise authorised by ATC, and at any flight level below 160 when an area QNH zone setting is 980 hectopascals or less. So, taking that official statement and demystifying it a little bit, it basically means that the pilot of an aircraft operating in New Zealand FIR must fly at prescribed altitudes or flight levels set out in the ENR 1.7-2. New Zealand FIR table of cruise levels, you can reference that, open up the ARP and you'll be able to read it. But to simplify, one thing I like to use is the nose. So north, odd, south, even, plus 500 feet. So VFR cruising altitudes when flying at a heading north, so 280 to 089, flying odd altitudes at 500 feet. If flying on a heading south, 090 to 269 magnetic, flying even altitudes of plus 500 feet. So if you're heading north, choose an odd altitude plus 500 feet. If you're heading south, evens plus 500. So some more terminology and principles. We define true and magnetic track as a true track required is the path we plan to fly between 2 points measured off our chart. We can then apply the magnetic variation to get the magnetic track required as per lesson 1 part 1. Wind velocity as a speed and also a direction the wind is blowing from. It's important to be able to distinguish that. It's not where it's blowing you to, but it is where the wind is blowing from. It is written as a 5-figure group, the first 3 digits being the true or magnetic direction, and this is important depending on the source of the information, and the last 2 being the speed in knots. I will get on to how the source of the information varies between true and magnetic, because you will need to know that for the exam, and also just general flying in head and tail winds. Headwind is a wind on the nose, reducing our ground speed. Tailwind is a wind on the tail, increasing our ground speed. It's relatively easy. Crosswind is the wind coming from either the right or the left of the aircraft, pushing it off the track required. We will get into that in detail later. True heading is the heading in relation to the geographical poles. So anything that's true is geographical. The track corrected for wind velocity and resulting drift, we can resolve the triangle of velocities to find it using our navigation computer. We do have a couple of slides on that. Magnetic heading is true heading corrected for magnetic variation, which we've already done. Compass heading is the magnetic heading corrected for compass deviation. Drift is the correction we apply to our track to allow for any crosswind. Drift is the angular difference between our heading and track. Port, which is left. Drift pushes the aircraft left, starboard. Right drift pushes the aircraft right. Planned drift is calculated using the navigation computer when we're doing a flight plan. You can make in-flight adjustments to this as you go, and hopefully not using an E6B. Track made good is the track that the aircraft travels across the surface of the Earth. This can be expressed in degrees magnetic or true, and you can make in-flight adjustments. The amount of degrees, so the wind correction angle is the amount of degrees that the aircraft's nose is pointed into wind. Effectively the same but the opposite direction of the drift. The wind correction angle is the angle you must allow for drift so that you will maintain your planned flight. Deduced or dead reckoning is having flown a leg, we are able to ascertain ground speed so that we can calculate how long it will take us to get to the next checkpoint, or we can figure out where we are knowing what heading and speed we have maintained and for how long. Track errors is the angle between the required track and the track made good. The track error will either be specified. Oh, my spelling is terrible. As a number of degrees left or right of the required track. So if we're going from A to C, and we take a point in reference at B, and we say, right, we just want to confirm where we are, and we find ourselves at D, then we have flown the track made good, and the angle between D and A, which again we can work out on the E6B, is the track error. So we've gone from the desired track to the track made good. We've defined what the track error is, and then of course we've got to have a way of working out how we get back to our destination point, which is C. So we'd have to work out the closing angle so that we can then repoint the aircraft in the direction that we need to go, which is the required track. So the closing angle is the additional angle or correction which must be made above the track error to regain track. If only track error is applied, we will parallel the track. Closing the angle is the angle we need to put us back on the track. So if we only add the track error in the opposite direction, it means that we will run parallel to our desired track. So we would need to take the track error and the closing angle in order to be able to adjust our course and heading to be able to get back to C. Estimated time of departure is the time we estimate we'll be departing. Actual time of departure is the actual time of departure, funny enough. Estimated elapsed time is the estimated time flown on each leg and how long we estimate it will take us to fly that leg. ETA, obvious. Actual time of arrival is the actual time we arrive at our destination or checkpoint, and it's the checkpoints that are key because that allows us to be able to break our overall journey down into legs and use things like the triangle of velocities to be able to ascertain what our route is and our track error and our correction angles. The 1 in 60 rule. Often overly complicated, but it doesn't need to be. We can do this on calculator, we can do it in our head, and we will have to do it on the E6B, and we'll show how to do that. So it goes as simply as, if we are 1 nautical mile off track after 60 nautical miles, our track error is 1 degree. To put this another way, distance off divided by distance gone equals the track error divided by 60. Important to measure all distances along the track required, not the track made good. On the navigation computer, all we do is we line up the distance off track on the outer scale with the distance run on the inner scale, and the track error sits above the 60 pointer. And I did have a couple of exam questions on this. One was pure and simply, can you define what the 1 in 60 rule is? And another one was part of the calculation in order to be able to fly a corrective angle back to our destination. So I've got a quick shot here of how we do it. So on the Navic computer, line up the distance off track on the outer scale with the distance run on the inner scale, and the track error sits above the 60 mark, or that big pointer that you can see on the left. So if you travelled 70 nautical miles and you have found yourself off track by 8.7 nautical miles, what is your track error? So in order for us to do this, we put 70 on the inner scale and we put that parallel to the 8.7 nautical miles off track, and then we look at the big black, some of you will have just a triangle, the other will have a 60 in it, and that points to what our track error is. So that would work out 7.55, and you round that up to 7.5. Great, wonderful, hunky-dory, and you would have passed that question. And you would have certainly been able to get to that rounding up. You'll be able to see off the exam answers that you're trying to work to that they allow for those differences. It doesn't get down to the 7.455 degrees. It'll be rounded up to either 7.5, or if it's 7.21, it'll be 7. But again, round up and round down, because of the E6B isn't the most accurate. It is to give you rough determination in the air. So the exams do allow you to be able to have a tolerance between these. So 1 or 2 degrees either side is allowed. The 6-figure system to indicate time and date. This includes the date of the month, the hour, and minutes. So 16 is the date of that particular month, and 1930 is 7:30. Now, a few things that we have to do is be able to derive UTC time from New Zealand Standard Time that we're in now, or New Zealand Daylight Savings Time, which we've just come out of. And we need to be able to jump to and fro, because everything that is involved in aviation will work to UTC time, as again we discussed in lesson 1 part 1. So UTC is the standard time used in aviation. All other countries reference their time using UTC, including us. UTC is used on flight plans, weather reports, NOTAMs, TAFs, METARs, and it used to be GMT. And despite that being a subtle difference, GMT starts hitting the daylight savings time problem as well. So UTC is the standard fundamental. We don't need to worry about the difference between GMT and, for anyone watching in the UK who's doing their air navigation and flight planning, GMT, UTC, you treat as the same thing. Standard time, so whichever country will have a standard time and a daylight savings time, and it's the time we set to represent non-daylight savings time. During this, UTC for New Zealand is 12 hours behind, whereas daylight savings time is the time we set to represent daylight savings or summertime, and during that time New Zealand daylight savings time is 13 hours ahead of UTC. Got an exam question on that, funny enough. We can add or subtract 12 or 13 hours from New Zealand to UTC, depending on whether it's daylight savings or standard time. These calculations can be tricky if midnight is crossed during your calculations of submitting flight plans, as you have to remember to change the date when writing your answers. And as I've said here, I have 3 questions relating to this. So one is UTC time on flight plans, another 2 questions on conversions of being able to do the 2. So we've just got a little table here. What I'd really like you to do, pause the video and work out from daylight savings or New Zealand's standard time. So on the right hand side I want you to do the UTC version of what you see on the left, and then convert the following departure times from New Zealand Standard or New Zealand Daylight Savings to UTC, or UTC to the other way. Pause the video, do your calculations of 12 or 13 hours ahead, but remember, check the date as well. So 12 hours ahead on, say, the first one here, 23rd of October, 11:47. All you need to do here is just turn that into the 6-figure dates. So 23 is the day of October, and 11:47 you just transfer that into the 24-hour clock. So do those 4, and then we'll do the conversions between New Zealand Standard Time and New Zealand Daylight Savings Time to UTC. Remember, you're looking at the dates then, which is the most specific thing, because if it's like the 15th of April at 9:11 PM, then, oh no, that's not right, sorry. So the 6:35 AM, the 9:11 PM, check if the 13 or the 12 hours exist and correct the date accordingly. Pause the video, do those, and on the next slide we'll give the answers for them. So here's your basic answers. So the first 4 are just a conversion into the 6 figures. And then just compare how you got the answers, and if you've got the dates wrong, just look to see why you've done that. We do have to do this on a consistent basis, and 3 questions on the exam is a big dent in your tolerance to be able to pass or fail. So make sure you can do this blindfolded. Good luck with it. Now hit the questions and answers for the revision of Lesson 1 Part 2. I have thrown questions in there that you need to be so okay with for the exam, because this is not the hardest part, but you don't want to do silly mistakes on this when it comes around to doing E6B calculations. That's where you really need to invest your time. So do the Q&A. Good luck with that. Keep doing it until you can get 100%, then move on to the next video. Good luck.